a lot of operations in parallel and so on. Like the brain is still different in a lot of ways from general network architectures because like the operations it's doing is probably different, and also like the brain is not a feed-forward network where it's actually doing different neurons are asynchronously doing stuff. And the actual algorithm is not grading the set, it's something else. Uh, but you'll
Yeah.
also find math results like better models of the brain, like Hopfield networks or whatever, are still equivalent in some sense to neural
Look at
networks
this,
or
this
whatever.
coding.
And you will expect to see some similarities in some. How much similarities? I don't know. But
Yeah.
like things
But
like polysemanticity, you will find also on the brain, and but those like just you have a limited set of synapses or weights or whatever in both cases, and you want to find some set of features. You want to compress features on those, so you kind of need to use polysemanticity in some way. It just doesn't make sense to use one single neuron for each thing. Unprivileged like the basis of each neuron, like the neuron basis, and you then find that the neuroscientists are also saying things like that about the brain, and it's not really that surprising when you actually think about it. Uh, but
yeah.
yeah, anyway, going. Also seems like everyone is kind of left at some point, and it's only me putting on that card. But let's keep going. I mean, to be fair, it has been already been 1 hour. uh,
Yeah. And
uh,
it's kind of start of the paper. Well,
yeah, true. I mean, we did. Maybe I should have gone quicker and skim it or something. We did read the. First, maybe I should read the paper beforehand. Uh, but also, we did read the summary at least. So at least people will have like a some idea of what the paper is about or what it's saying.
it's still faster than the different Discord because they yeah. Here there's more background for Mech Interp, basically.
I'm also curious about what you talk about on the different Discord. How much was people having to explain what the sparse encoder are?
Yeah, I went on showing them Neuropedia, for example, and like playing with
Okay.
that so that they have an idea, for
Okay.
example.
Like, did they just not know much about making terp in general to the point that like you explaining
Some
what
did,
making terp is and know what the sparse encoder is and whatever?
partially, yeah, they did.
Okay. Which one was like which server was that? What is like?
Yannick Kilker.
Yeah, I can see that. I expect people there know about interpretability. Don't like, know about machine learning, but not making terp in specific.
But they still exist there, so yeah.
Yeah, I mean that's cool. It's been a long while since I think I only been to one or twice to the in the Yannick thing, the server thing. I was once with the OpenAI BPT one because I was very interested in that paper because just before OpenAI released that paper, I was doing my master thesis also on doing training a transformer on Minecraft.
Oh, nice.
like because I was
Yeah.
because Wern had written about decision transformers, and I was like, okay, I will do something. I will try doing decision transformers on Minecraft for the Minecraft competition. And like, I was like, okay, so I looking at this. I look at there was some scaling law. I realized there was some scaling laws for that, and my models were just not big enough. And I was like, yeah, with these models, this will probably what was my conclusion and future work thing. And like, 1 month after that, OpenAI just made a much bigger model using the same kind of thing, but better, and just did it.
I hope they cited you.
No.
Uh,
I don't think my thing is even published anywhere except like the servers for my university or whatever.
yeah.
Anyway, let's go back to the paper. We can, especially because I'm still recording. Let's actually talk about the paper, and we can talk about my stuff after we stop recording all that.
Yes.
Feature reconstruction of new activations. Um, SCPC, next CPC. Okay. Character count spaces causal. Huh? Evaluation experiment. For an evaluation experiment, we zero blade. K dimensional surface corresponding to the top K principal components of the per character count mean activations and compare to a baseline of a blade in random K dimensional subspace. Before we measure the loss effect, broken down. Okay, so they zero a blade. Yeah, so they zero blade the dimensions and also random dimensions and find, yes, these dimensions are important for the output. This is just more evidence that this is just not some weird PCA artifact, basically. I like how it
Yeah.
looks from the very far away. Okay. Intervention experiment. As a result, we perform an experiment to modify the perceived character count at the end of the meaning. Yeah. Specifically, we see both the character count C and the distribution to the mean activation that correspond tokens so that is with count C. That is a patch igual a original minus I don't remember how this letter was called, but U original plus UC original. It's not U, it's whatever.
Wait, I also don't remember.
I don't remember, but yeah, the U with the weird.
Me. It's mu.
Okay, it's mu. Makes sense. Activation of. So this is just. Wait, sorry, I was not. I was saying it out loud, but not actually thinking about it. We simple character counts associated the main activations across all tokens in our character count. So they take all the activations. Prompt. Substitute the mean activation across all tokens in that is with count C. That is. Okay, so they just remove the activations for the. Okay. Average activation metrics of you. It is the average of the for that count. Okay.
Okay. So they basically put this count everywhere. The count C. Which can be.
But are they taking the whole activations for the average activations for count C on everywhere, or only okay, so they take the mean vector and also only the 6 PCA dimensions, right?
Interesting.
And both work. I mean, I will have expected that taking the style thing might break the model, but apparently no.
Interesting that you can just take the mean, like average activation, like the whole activation, that you don't need to do like some subtraction, as in like the original love vector, for example. You just get the difference between any prompt that has love and all other prompts. or many
Yeah,
other
because
things.
normally if you don't do that, you break things, but apparently here it just works, unless we are
Yeah,
missing something. Like I
it's
wouldn't
like
be as surprised that just the rank six thing where you're only taking the six-dimensional PCA thing space that works, but it is surprising to me that the whole thing apparently has similar results.
yeah,
But maybe it's because the like this task is simple and the model doesn't need to. It's only doing the count thing. So I'll put the new line or something. I don't know. Or maybe it's like on the layer. If you do it in a different layer, it doesn't. I'm not. Yeah, I'm not sure. I guess. No, wait. Actually, I'm curious where they get the activations. Like, is the main activations from what? Because triple per character counts, but on where? But if it's on the same sentence but with different words at the end, right? Then all of the other things will still be the same. But
ah,
if it's different sentences with different words at the end, you would expect a lot of different things are different and they will break in different ways. Uh, yeah, I don't know. I get confused about that, but let's not
yeah,
spend too
me
much
as
time
well.
about this because we are going to spend 3 hours again probably, and let's
Yeah,
try to let's get through the whole thing.
this is relatively minor.
The pro perspective. We try and supervise logic regression to predict the counter count. I think still so far I think we have found some things that if I was going faster we wouldn't have seen, like the biological stuff, which is pretty cool. Uh, Probes trained after layer 1 achieve a root mean square error of 5, indicating some intrinsic noise in the character computation. These features have relatively wide perceptive fields. These components capture 82% variance. So this is saying they try to do probes and they have some error layer 1 and they take this as the model not having always like perfectly accurate representations of the count.
Yeah, 82% of the variance.
Yeah, that's a different thing. This is the PCA that the 6 dimensions are 80%. But up here they're talking
All
about
right.
just the probe having errors.
Trained after layer 1 achieve a root mean square of 5.
We look at
Intrinsic
the
noise. Hmm.
response of each token with different characters, we still static patterns. In addition to diagonal bands, probes like sports features have interior representations, which it should find those diagonal ones on each side. The response curve each probe is not monotonically decreasing for response but rebounds. This range tends to be a natural consequence of embedding a Reaper manifold in low dimensions. Oh. Uh, that's cool. I think I've seen some things on my, like when I was looking at a tiny, like modular multiplication model that looked like this, and I had not, and also look, you see it on the when you do cosine similarity of the. All right, that makes sense because the you are seeing. So you
It's
have a linear.
sinusoidal again.
I'll have to. maybe we'll see what they say, but I think this is maybe like, so you try to do a linear probe in something like this, right?
Yeah.
If you imagine taking a linear slice of this, if you get this thing here, you're also going to get a bit of this one, like when the thing spirals back to this direction. It's
Yeah,
sliding
this
on
makes
some
sense.
other. Yeah, I think this is that, but maybe
Yeah,
I'm
it's actually
getting
lump.
confused and it's something else. But I think that this might just be that.
Yeah, that it's sinusoidal again,
Uh,
but
linear
it's like
factor.
less dimensional. Okay.
No, yeah, that other linear picture also. Yeah, I mean, I say this and it sounds to me like it makes sense, but don't. I'm not sure. I might just be saying something that sounds sensical to me, but actually, but actually, the actual answer is something else. That happens when I read papers. So. uh,
It's like it's basically the same structure they found earlier, but using different tools.
no representation to this. We noted cosine similarities of the mean and derivation vector. The linear probe vectors and feature decoder vectors are exhibit symmetry ring in patterns of the available feature. Are there neighboring features not orthogonal? Features for terabyte had negative similarities, and the others even for terabyte had positive ones. So on. Okay, yeah. So this is just saying they found this thing where yeah, this is negative, positive, negative, positive, and you see this and see that this circle. So yeah, I did find this pattern on the modular multiplication thing, and it turns out it just represents like the same way as the Neil model. It also represents things on a circle, and you can take the Fourier transform and get the circle, right? And just when you plot the cosine similarity between numbers, it does look like this. And it's like so where is more similarity, less similarity, more similarity, less similarity, and that's because it's the circle where it's like the like 80 is more similar to 30 to the numbers that are around here, but it's less similar to the numbers that are here because on this, if you are taking lines on here, it's like the circle goes back around. So at least in one dimension, you are the same. You have the same thing.
Yeah.
This structure turns out to be a natural construct have a desired pattern of similarity. Trivially achieved in 150 dimensions, projected down to low dimensions. Huh. As a toy model of this, suppose that we wish to have the discrete circle world of unit vectors. It's similar to its neighbors, but orthogonal to those for the way. This can be realized by a symmetric set of unit vectors in 150 dimensions, with cosine similarity made is pictured below. Okay, so the ideal similarity matrix is this, where each thing is only similar to each other. But when you are doing a lower dimensional approximation, you get this, and you get something like this. I'm sure I understand. I want to understand this because it seems like it's a math explanation of why there is so many circles. I don't know. Projecting these to the top 5 eigenvectors yields a 5-dimensional embedding of the same vectors with the cosine similarity matrix exhibiting ringing. We also plot the curve these vectors form with the top 3 eigenvectors. We cannot speak of the original 150-dimensional embedding of the circle as being highly curved, and the resulting 5-dimensional embedding as sustaining as much as curvature as possible. Embedding of the circle with the 3 variations.
So
And it's like completely understand. Okay, so this is saying that if you have a set of unit vectors in 150 dimensions that are just orthogonal to each other,
Um,
right?
there's the ideal similarity matrix,
Yeah.
and I should similarity matrix should have each one be like cosine similarity matrix between the first and second, like first, second, first, third, and so on.
Yeah. This
I'm
is
not,
just the each one to each other,
yeah,
right? So
and then the
this is just saying that all the numbers are orthogonal to each other. All the representation of the numbers are orthogonal to each other, and there is zero similarity between each of them. So this just each one is just similar to itself. Uh, but this is saying that if you take something like this, which is just some metrics with all of the vectors orthogonal, and you try to project it into a five-dimensional thing, that gets you some kind of curve.
I wonder how the operation of projecting this to its 5 eigenvectors looks like. So like top 5 eigenvectors. So you take top 5 eigenvectors,
I feel like
and
I
you
need to
take this
review
matrix and multiply
to
it by
Brown,
the,
whatever the YouTube channel was named, the
yeah.
videos on linear algebra.
So you take this matrix, take top 5 eigenvectors, and then apply this matrix to these top 5 eigenvectors. Why they don't show equations? That would be simpler. Well, projection is like matrix multiplication, so
Yeah.
these two, it's top 5 eigenvectors. So you multiply, so you take the 5 eigenvectors, which are just vectors, and each of them you use this transformation, this ideal symmetry
Yeah.
matrix to them, and that yields a 5-dimensional embedding.
Yeah, I still not get why if you take some like I imagine a bunch of 150 dimensions when each vector is just one dimension is one and the others are zero, right? Like could be another shape, but that's the simple way to think about it. Why, when you project this to 5 dimension inner being this curve thing? Uh,
Each eigenvector should be also 150 dimensions, and the
yeah,
matrix
like
should be 150 times 150.
but are they what? So, where are the eigenvectors geometrically?
Well, eigenvectors are like visually like when you take the when you take the mat when you take the matrix and the directions where it's like if the geometric projection was like just like stretching basically.
Mm-hmm.
So like that's part of the matrix. That's like what eigenvector is geometrically. Uh
Like if you have a set of 150 vectors that are all orthogonal, let's say they are one in some dimension and zero in the others. What is the eigenvector? What are the eigenvectors that?
the vector should be just the okay. The vector should be just n. So in this context, it should be just like those 150. Like,
They
can
are.
eigenvectors be more general than this? I always found eigenvectors as just like a vector.
Oh, maybe it's less than. I think there's less than 150.
Yeah,
I don't know. I need to review
yeah. It's
rewatch the
like
videos and what the geometric interpretation of eigenvectors was.
yeah, like eigenvector times eigenvalue is like if you stretch or if you like shear like these simple transformations that you can decompose matrix into. Just like if you took the vector and multiplied it by the eigenvalue.
Anyway, let's keep going, I guess.
But I'm confused
Okay.
about the dimensions. That's what I'm confused about. Yeah.
We can keep going and go back to this later if we have time.
Yeah.
It matters. But like, I do prefer to at least have read the entire thing.
Yeah.
Alternative
Can ask.
one can
Yeah,
view the ring from. Sorry.
go ahead.
Okay, yeah. For the expression code feature decoder, such a kind of inference weight, with no capacity constraints, the model may use orthogonal vectors to represent, yeah, the responsive to the input item. In order to put them in lower dimensional superposition, the similarity matrix is both a wider diagonal shape and the upper lower ring stripes. I construct a simple physical model showing that the rippling and ring and the solution is found dynamically, where many vectors are packed into a small number of dimensions. So what I'm getting from all of this is there is some math reasons I don't understand yet. That why if you want to pack a lot of vectors nicely with in some superposition with not a lot of dimensions, you want to do some kind of curve thing like this. And they have some physics models of how that happens and all that. 100
Yeah.
points, 2 points express the gravity force to the six closing neighbors on each side. So they want to be close to the similar numbers and repulsive force to other points. And wait, I modern procedures where we use the probability of six into an interval. So yeah, they are basically doing the same thing as the modular addition thing. This is kind of more for modular addition in that it's a circle in the last number connects to the first number. Okay, in this actually with this, I can see an intuition of why this happens on the thinking about it in terms of the physics thing, right? Like I can see why if you do a thing where you have a bunch of points in some set of lower like say 3 dimensions, right? And you want them like you want the close ones that represent similar numbers to be close to each other but separate from the others. Like the nine, I can see on my mind how that they separate and in some kind of circle.
Track neighbors and repel distance
Yeah.
points. Oh, I can choose between an interval and a circle in this playground. That's nice.
Yeah, here like the circle is. I think what they mean is like the last number, like a fundamental thing is next to zero. So it's like the modular addition example when it takes a circle instead of like a spiral, which you get when you don't want to connect the ones.
Yeah. The simulation can
That was.
sometimes.
Hmm?
Uh, yeah,
Oh, sorry. What?
there's a footnote that
Okay.
the simulation can sometimes find itself in local minima, increasing the width of the attractive zone before decreasing it again usually solves this issue. Interesting.
This is a circle, but I do wonder, like, at least on the physics thing, I also don't see as obvious why. Like, if you have the thing that is an interval and the borders are not connected, uh, why you end with something like this and not aligned, right? Because this will still, like, this will repel this. So I don't think why this doesn't kind of straighten out. Uh,
Because they still attract, the nearby ones attract. And that curves it.
because right, because this one and this one are still a bit more attractive than the next,
Yeah,
like the next circle. So you still want, yeah, you put
yeah.
the things similarly. You still want the, yeah, makes
And
sense.
in the simulation you can switch to interval as well.
Oh,
If you go back to
one,
the
yeah,
at the top, you have like speed, zone width, dimensions, topology,
oh, cool.
and play and so on. It's like interactive. So you can
Uh,
choose interval at the right. Yeah.
yeah. Oh, it's like, let's
Yes.
reset.
Yeah.
Oh, nice. Yeah, I do have a plot. I'll show it later on after the reading, but I do have a plot in my project that looks like this a bit for the modularization thing. Okay, so it does get into this kind of twist. I just speed it up. Let's see.
Almost made a circle.
Yeah, this
Oh
one is
yeah.
kind of.
I, I made a perfect circle.
Oh, nice.
Everything has to be maxed out. Okay, and that will just create circle by default. And has to be, yeah.
If you increase zone width, it does this. Also, so this is also wait. So what's wrong with in the model actually?
The less zone width, the more it tends to
Yeah, but like
twist.
in the model, what is like the equivalent to zone width? Is it okay? So
I think the area of attraction or something like that.
there's some dimensions, and you imagine. So the zone width is
Attractive zone.
how. Hmm?
It's attractive zone. It's in the footnote, the 15
Okay.
footnote.
Yeah, but what's the attractive zone like? Uh,
I guess the bigger distance, the less attraction. Like they just calculate for each point like the distance, and the closer the more attractive. Which would make sense because if you turn the zone width more, then you see how all the nodes are much closer to each other, and when you make it low, then everything is much more distributed. Yeah, so it's like attraction.
So this is just where, like, how long they like what the distance they attract each other.
Yeah. Okay. So it's always the same attraction strength, but just different like the amount the area.
English names for. There's a bunch of other examples here which is cool, like English names for colors, which are like yeah, and years of the 20th century. Dates of the year. It's all circles.
Yeah. But
But
it's
I guess it.
I really love that they have this physics model of this.
But
Yeah.
I do get here intuition for how the reason there is so many circles is because that is what you get if you wanted some lower dimensions, when you want to represent, you want to have a line where you have like the things that are the things are on what you have some dimensional variable like years or whatever or dates, and you want to fit it in a lower dimensional thing where things are closer to it, where the nearby like years or whatever that are close to each other are close to each other, and things that are far apart to each other, and you have some limited space and dimensions, so you end doing this like this kind of curve thing.
Yeah. Like I wonder like when these shapes form using the attractive forces, like to what degree does it correspond to how the features form? If it's also like this smooth attraction between the different features, or
Yeah, I mean, here they have some examples of like actual models that
and the result is the same, but I would assume, or the process of getting there might not be might
have.
not look exactly like this
Yeah, yeah.
attractive, but it might.
Yeah, I don't know how analogous it to a extent. Uh,
Yeah.
Even if it's not the same, I do think there is some, like there is the underlying reason why both the physics thing and getting the center end up making these shapes, but like they are the shapes that minimize some distance while maximizing some other distance with some constraints. Like, uh,
Yeah.
like both this physics thing and the gradient descent are ways of solving this optimization problem, how to pack things presentation of this lower dimension, and both get this. And maybe that means that human brains will also have this kind of things. You find this kind of curves in human neurons or whatever, because they also have to solve the same problem in some ways. Like maybe, I don't know, place neurons or whatever, you find that there is some curve or whatever. I don't know.
Yeah.
I I mean, at the same time, human brain I think does a lot more sparsity, so I don't know how that works, what that changes. Uh,
At the beginning, everything is noise in the neural network, and these structures form. Yeah. Like when we went previously over the evolution of features paper, I would love to see like more visualizations like this of the features forming into these different shapes as the model
mm.
trains.
Oh yeah, it could be cool. Do they have like, so this is the first model? Do they have something like that for the actual model? It would be cool if they can
Modular addition
do.
seems to be the simplest. I wonder if you could plot that beautifully.
Oh yeah, that would be cool. Like taking the uh, all the features for the. Well, you can plot, like I have the modular multiplication thing that has the same structure as the modular addition on the embeddings, and I have plots I can show later of I was plotting on time, like no I think you can see I don't have something like this, but I have something like this one, right, or the size similarity one, and you see some nice thing of how these things start up. here. Although I was doing an extra thing, I was not actually looking at the model multiplication for me. I was looking at an extra structure for me, but that's another thing. But I think I could plot it anyway. Maybe that's interesting. But yeah, going back to this. Yeah, let's keep reading.
Yeah.
I think the at least like we are not going to finish the paper. Maybe I need to pick less interesting papers for the day. Sensing the line boundary. Studying how the character counting representations are used to determine the current line of text is approaching the line boundary. To detect the line boundary, the model needs to determine the overall line width constraint and compare the current character quantities. Like I mean, at the same time, I do have. I think I already have answered my main questions about the paper, which like how they found this, which is just they saw like the features on this and say and manually thought, okay, yeah, this looks like it might be some kind of they reason out this and figure this out manually, and they don't have. There is no nice way of figuring this.
This is just like one part of the circuit. Then there's like the rotation of the manifolds and the whole circuit. Yeah.
Yeah, you kind of there's not even a lot of line boundary. We now study character representation of the line boundary. We find the new lines tokens have the other the character counting features that is based on the width of the line, counting the number of characters between arches and new lines. Okay, that's nice. So you have something that says the previous new lines were that length, because it is probably usually the case that there is some line boundary, like here there is a line boundary, for example, on this text, and it makes sense that the model on each new line counts how many characters until the previous one, because it's usually around the same thing with some exceptions where you here end the sentence and you could do new line. To be the previous, we train 100 people for it. Possible value of character code. So it's able to grab with the attention head with activates the boundary attention features. Individual sets with first components of the join PCA and the receiver stream and the receiver. Yeah, so they do the same kind of thing for the new line count, and they get the same kind of thing. It's a spiral. It makes sense. Within the set tweaks the character count manifold. Oh wait, character count probe.
They say that they using the attribution graph they identified the attention head, so they trained the cross-sparse transcoders on both the like MLPs and the attention. Okay.
Yeah, nice. So wait. Falling. Never mind. My parents are there, so I think. Wait, I don't know. Well, anyway, this color again, I'll go respond. Character count. Okay, so. Okay, so this is interesting. So earrings. So they have the character program probes and the line width probes, and the attention head twist the character count manifolds and the character count twice aligned with the line width k is igual a e plus e, no sé what, epsilon here begins. This causes the character to attend the new line when the character count is just a bit less than the line width. They have indicated that the boundary is approaching. This allows the current numbers to detect approaching line boundaries for arbitrary line widths. Oh, that's cool. So. So They have
Oh,
the character count manifold. Wait, the character count manifold here for what? For aluminum or whatever the next word is.
They say it's quite general, enables this head to detect approaching line boundaries for arbitrary line widths, so it doesn't have to be aluminum.
Okay. Yeah, but line width, like we did for character count. Okay. But character count was the word.
What are you trying to figure out?
Okay, so here line character count at a given token in a prompt to be the total number of characters into the last level line. Okay. Yeah, and what is the line width? So the line width.
Yeah, the line of the width of the line that it's in right now. So that's like fixed. So the sentence, like that's my understanding. So, yeah, because to get
Oh yeah,
if the
is
character
no, the
count
line width
approaches.
is the previous one, right? So wait, I think let me so the model lets to determine the yeah.
Line width
The
constraint, yeah.
name tokens have your dedicated character content filter relativity based on the width of the line, counting the number of characters between one adjacent lines. So I I understand this as you take the line width, like this line width thing is from the previous, like the last new line. There is a thing of how long that sentence is, right? And the character
That's
count is on the current line, right?
I'm not sure about that because as you approach the line width constraint, so like let's say you're on a sentence which has 10 characters. So as you approach the line width constraint, so like count, you're at character count 5, 6, 7 as you're doing autoregression, 8, 9. Then you're like at character count 9, while the line width is still 10. Then those are similar, and this triggers this. Like then it also like aligns those two manifolds. So the character count manifold and the line width manifold are like in the same direction, and you can see this equation that it's the character count I plus some error equals the
Yeah, I
line
just
width.
saying the line width is just a calculation of the width of the previous line.
I think it's the current line, not the previous one.
No, I think that's the
Otherwise,
character count.
the line width is a constant. The character count is dynamic.
Yeah, but I think you calculate the line width by seeing the length of the previous new line.
Okay.
And like, okay, so what I'm saying is, here it says, we find that the new line tokens have their own dedicated character counting features that activates based on the width of the line, counting the number between adjacent new lines, right? But that's the that's on the previous, like the ones that you already have. Like you have already a new line token written on the text, and it has a count of how long was since the previous new line, and you are writing a new sentence, and you have a character count for this. The maybe character count is the total character count of the sentence, and okay, yeah, I think I will see what you mean. I don't know. I guess it works
Those
either
are
way.
different counting features that you're describing there. They have their
Mm,
own dedicated counting features that activates based on the width of the line. But the width of the line is still fixed.
okay.
Counting the number of characters between adjacent new lines.
I mean, okay, it doesn't matter that much.
You may be more right than me.
I know, sir. Doesn't matter anyway. The way is, you have the line, you get the width of the line somehow, like the max, the one you want to compare to, and you twist the current, the character count to match with it, and see if it matches with this part where whatever the width is.
Yeah,
Right.
plus some error, so that the head attends to new line where the character count is just a bit less than the line width. And indicating that the boundary is approaching, and creating new line symbol.
So you you get this and you compare them. This is just doing comparison by putting then the two things together.
Yeah.
And then you multiply them and get a lower number. Sorry, you get a higher number if they are close and lower number if they are. Makes sense.
Yeah. Good product.
Which, if you were doing the discrete thing, you can see this as the numbers match to each other. Like you will see that this has cosine similarity with this independently, and see, okay, so they multiply together and you get a high number, and you will be like a big table that generalizes. Just you can also see as this spiral where the things are close together.
Yeah.
Yeah, that makes sense, because you have the line width. You are not comparing to some fixed line width. You just have some line width variable that you represent at some point on this thing, and you compare it with some point of the other thing, and you multiply it together, and that's it. So this works for even bigger. This works for arbitrary line width.
Yeah. In the footnote, they also add two arbitrary kinds of separators as well.
Yeah, as long as you have some part of the model that so on the OV circuit, you could take for you could also in other kinds of operators store the same information, and like this or store the line width and use that. Makes sense. The model I don't doubt the model re-implements all of these for different separators. Just use the same listing for all of them.
Yeah. I wonder if it's all happening at one place in the model.
I mean, it's distributed between different attention heads and whatever, but probably at the same layer, right? Maybe.
Yeah, the different attention head looks like right above what we just looked. Like they look at like this. Oh, they seem to be unified. Okay. They have this sinusoidal pattern.
I think it's always making noise around that. But anyway, so the resulting probes for character count I are similar line with probes, so probes line with probes. Okay. Okay.
That makes sense.
So this, I think it's okay. So this thing is a single attention head, apparently. We find that the model actually uses multiple boundary heads, each twisting the manifolds by a different offset to implement a kind of stereoscopic algorithm for computing the number of heads remaining. We attach more visualizations of boundary heads in the appendix. Ah, uh,
There's more spirals.
more spirals.
Or I mean helixes, not spirals.
Well, yeah, whatever the name is.
Yeah.
Low-dimensional curve manifolds or whatever.
Yeah. That's a much more general
Low-dimensional
term.
well, it's actually one-dimensional curve manifolds that are embedded in low dimension.
Yeah.
But yeah, I think the also there is two things over there. Ah, yes, Neil. Okay, I see Neil is posting stuff,
He's
but
announcing.
yeah, I gave Neil a role that is called Neil Nanda to let him announce things.
Yeah. That's ultimate permission for everything.
Uh, but yeah, anyway, so I was just going briefly here to say that there is something that there is something here that is not like on the. We'll see maybe this another day. But there is here. This is not the same kind of thing. There's a different structure. It's not. It's not dimensional. Is the thing.
Yeah.
So this is like a tree. So you can't represent it in one dimension because the relationships are not like what I'm getting from this paper is that if you want to a single variable where the relationship with it, want to represent things where the relationship with this thing is one thing is connected to each other and separate things other things are separate for each other, you get some kind of circle like this, and you if you want other find two kind of other structures, you are going to find things like the file of the 93 where the relationships are more like a tree, so you get something like this.
Yeah.
Variant multiple boundary heads. Uh, and this is all related to also on the anthropic thing for module. I was already saying this when we saw the first anthropic paper with like the transcoders paper where they did the attribution graph for the first time, right? That some of the things on their math, like I think it was multiplication or something like that, looked a lot like, oh, no, I think it was addition. Like the addition thing looked a lot like, there was graphs that look like this, right? That look a lot
Yeah,
like
yeah, yeah.
they were taking discrete slices of like some more, some kind of spirally thing. Like some lower dimension, well, I'm not going to say it.
Yeah. There are definitely I think some of the other paper I posted yeah, this that I posted last week basically shows this spiral if it loads. Yeah, it's up in the history. Yeah.
Oh yeah, yeah. That's always already. But I just think there was in the attribution graph paper they didn't find this. They were looking
Yeah.
at only attribution graph, but the attribution graph did so look to me a lot like there was something like this. They just didn't found it because they were
Yeah.
using transcoders that take take slices, discrete slices from this, and you get weird things like you have some slice that activate some on like numbers that are multiples of that ending 8 or whatever, and that's just you have a circle that turns around and goes back to be in the same direction on every time 10 twists or whatever. Yeah.
We're
Uh,
coming back to the
so
addition circuit. It's so convoluted.
everything comes back to addition.
Yeah.
uh, I mean, this is counter is also related to addition. It's all numbers.
Yeah. Here they show that the heads also like discretize. but those are like head directly from the model. Therefore, the model itself is discretizing. It's not just the
makes sense.
transcoders.
Because it's also like also on even the modular addition thing. The model is not, it's just doing things with integers, right? It doesn't learn all of the things on the middle. It just kind of hard codes the points on the circle for each integer, yeah, right? It just learned the sine and cosine for each point. I didn't. It doesn't work for floats, for example. If you train it with a lot of floats, it will learn some more thing that generalize to all of them, to continuous or something, or approximate. Well, probably approximates in some way. But if you are doing kind of like, the model is likely going to have to do some discretization because it has finite space and it's not like it has finite infinite precision or whatever.
Never of a function approximator.
At some point, you're going to have to want to separate things with relus, and that kind of has to do some kind of very sharp separation right there.
Yeah.
Anyway, the pseudo stream proofs for character count y are maximally aligned with proofs of line proofs k when I equals k, but not highly aligned in absolute terms. The maximum percent same is 0.5. Oh, yeah, we were saying that the best multiple potential heads actually kind of we will get back to that. Let's kind of want to quickly skim the rest of everything before going back to start, because otherwise we're not going to finish. Okay, so rest terminations, geometric computation, categorical, the model marking is with the counts. Apply the process of context. Okay, so use an enormous dynamic range. Yeah. Team fair solution. This is interesting, but we'll go back to that. Oh wait. Okay, this is very. How did we finally find this authorization? We saw several ledgers from the previous new line features and embedding to predict new line features. UK attribution showed that the top K feature was the previous line was 2060 characters long, and the top K feature was current character count is 3550 features. At any one time, there were often multiple counting features active at different strengths, suggesting that these features might be discretizing a manifold. Yeah. Okay, so it's like this. That kind of thing. But it's in the new line. Break suppressors features. We totally activated the next token will verify on the line, hence the weight prediction on the line. The break predictions and suppressors come in different frameworks with preview. Okay, yeah, that's nice. So they have.
Yeah, I remember this. I was fascinated by this.
You have things: model detector, break predictor, break suppressor. Right, cool. Here it modifies token before the one. Okay. Yeah, because 0, you can always put 0 with tokens. Yes. We fit on the line. How is the break feature above constructed from the boundary detector and network features. So they do the PCA, and a lot of this is just we did the PCA and look at the thing.
Yeah.
It's not a bad technique, I guess. Version geometry. I guess at the same time it only works because there is not that many. I guess you should expect there's new features, but if you have something that is like 10-dimensional and all the 10 dimensions are other, you're mainly going to have trouble putting it in your head if you have a PCA.
Yeah. That's one limitation of this approach. You can only imagine 3 dimensions.
Yeah.
I wonder if in the like there are some methods to visualize higher dimensions, and I wonder if like future Mech Interp papers will be using those.
This was learned with character defining. At least this is a better problem to have than like especially neuroscience people are not really thinking about this because they don't even have like are that clear on what the represent like the activations and representations are.
Yeah.
And it's not like you can even read them that efficiently. Maybe like you can get some from mice and whatever, and that's how you find place neurons, but it's not like they don't have great tools. I don't know. I don't know that much neuroscience anyway.
We can
Anyway,
ablate much more easily, do much more experiments and so on, and have access to everything.
Precisely this completely leveraged that reminds me of like David Bow trying to convince his neuroscience students to go to Mech Interp.
Yeah.
Anyway, let's try the standard state. Let's say by performing a PCA the combination of mean vectors, we see that the two counts are against orthogonal subspaces with only moderate curvature. So they do next token length and character remaining. Okay. So the model puts these two things on two lines here, like it untwists the thing and puts them on two lines arranged like this. So then it can just like each point is a combination of these two dimensions. So it just can make a line through it and say things over this line and things that are here. Oh, that's really cool actually. I don't know if I explained correctly and you understand it, but I think I get what the model is doing here.
Like I get that it's putting it like this, but how does it construct the line break? Like when it gets
No, because with line break once it has
characters
wait.
remaining.
So it must untwist the thing into this less well it's still curved but it's still kind of not right. It's close enough that it can put them like this. It can just twist into this, and then it can just use a relu to do this separation.
Oh, so it like finds the intersection when they are equal by that line. If the next token will fit on that line.
It can
I see now. Because the right is like the next token length is bigger than the character remaining. So that means do not that means you can do line break now.
Yeah.
But if there are the other side is 8 characters remaining and next token length is like 5, so like you can still put a word there, therefore you can put a word and suppress the new line.
Yeah,
Okay,
like
I
if you
see.
see it, you see it like it's just doing this plot, like it's putting one dimension like this and one dimension does this, and making this line here. It's
Oh
just
yeah.
doing the same, but in the space. But it's kind of
Okay.
a bit weirder because it's crossing. It's not just putting one here and putting one. It's crossing both a bit. But it still works. Like you could imagine shifting this here, it will be like the same as the graph.
Yeah, the graph is better now.
Like I didn't realize that the model is doing like the same thing. Like it's doing something that's like putting things on a graph, right? And making a line on the graph.
Yeah, it's doing linear regression. Well, no, it's how is this called? Uh, super vector machine, kind of.
I mean, it
I
kind
think.
of has to. I think it needs to use a ReLU to do this sharp boundary. Well, not necessarily actually, because it can do. It could do just like it is just a line. Could be do a number that's higher here and lower here. It can just add do a. I'm not sure what operation you do, but yeah. No consider the progress simulates possible. Made trivial by the the prediction to break the line is made trivial in the geometry.
I think you can do that just with matrix multiplications. And at the same
Yeah.
time, I wonder if like break suppressor is in a way the negative of break predictor. Or if they are like more disconnected.
Mm-hmm.
I would assume they are like inverse of each other in the latent space. Or negatives, I mean. Yeah.
One could imagine a more general matrix where the model comprehensively reduces the probability mass from all words that sets the line limit to the new line. Okay, yeah, Claude doesn't do that. Okay, so it. Yeah, no, Claude doesn't do this fancy thing. It just Claude Haiku just increases the probability of the new line directly, and doesn't do the thing where it then decreases probability of words that are longer than the new line. It just if the next word is likely going to be bigger than the new line, it increases the probability of the new line.
Hmm.
If I understand
Yeah,
it
that makes my
correctly.
understanding.
How many describe how the various character count representations are used? The last big remaining question is how are they computed? Also, I don't think it's so obvious that the other mechanism is a good idea, right? Because you are going to put a new line or not based on what the next word you expect it to be. So maybe I'm misunderstanding what they are saying too. Never mind. Let's keep going because otherwise we are not going to and actually finish this. A distributed character counting algorithm. Having discovered how the parity content representation are used, the last big remaining question is how are they computed? We will show Haiku uses many attention head records, multiple layers to comparatively compute an increasingly accurate estimate of the character count. This sounds to be the most complicated mechanism studied. That there are many similarities to the boundary detection mechanism. Aha. Okay, so this is the part.
Yeah, I didn't understand this part in the paper.
Okay, I understand at least from this part that this is the part that we were talking about earlier, where the model has to know how long a word is, like count the words, now, like know how long each token is, and then add them together, and that's kind of very non-trivial.
Yeah.
I don't think it's just a lookup. So first might be a lookup table, but then you need to also do the steps that you might be repeating. You have a bunch of counts. You need to sum them. Like you have one. This word is one. You need this word is three, and this word is five, and you need to do addition of. Okay, so the total length of the sentence is 1 plus 5 plus 3, where you don't have addition as a base operation of your thing. The basic operation is matrix multiplication, so you need to add the character counts with multiplication somehow.
Mm-hmm.
Okay, so intuitive understanding behavior heads projected outputs into the PCA space of the line character controls. Layer heads, 0 heads, each write along what appears as an array when previsualized the first covers components. This sum generates a curve. Is the sum generates a curve manifold? Array means it's just a line, right? So,
Yeah.
okay, so they have a bunch of lines and they add into this curve. Where you have these. I'm curious how you make curves with a bunch of. You have a bunch of heads where the activation is some, like they combine them to get this, where it's like you have different vectors. You're kind of drawing the line with different attention heads.
Interesting. Those are like the most basic that you then sum to get more complex manifold, while the other heads are more granularizing in a way, more curving it more specifically, and you get even more complex curve, and all of that interacts somehow. So it's like different levels of granularity, maybe. I don't know.
I don't completely get how you get from lines that are. If the lines were different numbers, you could draw that. Yeah, I don't completely get how you get from lines that are all in the direction of the numbers, right? And how they combine to make this.
You sum them.
Yeah,
it's like you
but
sum head 55, head 1 for 55, head 0 for 55,
yeah,
head 2 for 55, and then you get that point.
this adds to this circle. Okay, I don't get a good in my head why how different lines will make different curves. But yeah, okay. Anyway,
Each color is a different head, right? Or
yeah,
is
it's got a different head. Like you have these
Yeah.
lines, and they get added, and that makes this curve.
I see. You're asking about the more fundamental mechanism behind the circle itself.
I feel like this is a simple geometry thing. I don't don't have this
Like
good intuition. So.
I'm like imagining of like if you go continuously, like
Yeah.
then you can see how the shape is discontinuous and slightly curving, depending if you like do this continuous summing. I don't know. I just visualize it as like constructing it point by point. Makes sense to me that it would curve like this.
Yeah,
Because
like
it's
if
like
you add this point and this point, it will be here, and then this point and this point, it will be here, and this thing is the upper thing. Yeah, I guess that makes sense. And this
Yeah.
probably makes it twist slightly.
Like you can kind of or like
Okay,
you
no,
can
I think I see it now. If I just to take 2 dimensions for starters, I can see how the sum of these 2 dimensions is always some curve like this.
you can also see this like at the different ones are like at different attractions. Or I don't know if that's helpful. Like different pushing in different directions continuously.
It will be here and will be here, and it will be like this if it was the sum of this, but this other thing which makes it twist.
Wow, the
Okay.
blue one is really messy though. The end. It's like packed together lots of at one place.
But okay, so if it has only the red and green one, wouldn't it just be like here and plus here? If you imagine doing addition of these two things, never mind. Not going to bother spending too much time on that right now. These lines, these heads make this shape, and when you add them, like these vectors making it. Well, we believe that. And okay, so layer 1 heads instead output curves which combine to produce an increasingly complex manifold. They appear responsible for sharpening the layer 0 representation and thus the estimate of the count. So you get curves that are made like this, and then you combine them, and there's this other thing.
Those are layer 1 heads, I see. And those are layer 0 heads. So like the layer 1 heads got the curvature from the layer 0 heads, and then they form even more complex manifolds. Okay. So it's like this composition of making more and more complex manifolds.
Yeah, but this is okay. So this is already the count, right? As I understand, it's the count of the words. So we need to get to the embedding to know how this layer 0 thing is made, because this is already, I'm guessing, doing something with embeddings to make this, right? Like these heads are probably already doing something in the attention with embedding of each token to say this token is that length and this token is that length, and you do this operation and you get this total count. And you put them on this line.
What are the differences in the layers? Like,
sorry.
Differences in
what
the
are the
layers?
differences in the layer? Yeah.
You get more and more curved.
Like, does that also happen for like future layers? Like, the layer 2 will be more curved.
That would be my extrapolation.
Okay.
Find the air count of current position of the K5 key layer 0 heads. It's well, I don't know if it's starting more cool, but it's a more approximated thing. This is the correct spiral, right? Like it's making more complicated curves and adding them until it gets the correct thing.
Yeah. Since the R2 is like not increasing that much.
R2 for the character composition of the. Okay, so at some point it just has the correct thing and it doesn't increase too much. Okay, embedding geometry. To start from the character completed, we start at the beginning the embedding matrix. As before, we can train probes or compute the average weights for every distinct token length in the embedding. We visualize the token character count for probes or character length, and visualize the top principal components. Using the first 3 principal components, we see that the embedding character counts and arrange in a circular pattern with a selected component. Okay, so the PCA is carrying this paper.
Yeah, that's also my
We see that the embedding character counts as arranged in the circular pattern. Okay, so it's more circles in there, but this is on the bedding, and the model just hard coded this on the bedding.
Yeah.
And yeah, this is forward. This is from 0 to 14 because this is the character count for a word. Like the 1 to 150 is for a sentence. Well, for a line, I mean, sorry.
Yeah.
And yeah, like this is. I expect there is more complications in this because some words are not a single token, and there's probably more complications you are ignoring here. But never mind.
Yeah, that's also interesting how like the longer the character length, the closer it gets again. So it's like the distribution of the length of the words in there again. Isn't that the Zipf's law? Zipf's law, I think. Also, I think so. Like all
I'm
these.
not familiar with Zipf's law.
Isn't this like the opposite of like where the longer ones are less rated?
Yeah,
There's
well,
a lot more words of this. Like there are more words of these ranges than on these ranges.
Maybe.
Oh no, actually no. Maybe there is more words on these ranges, and like they're more separated because you need to distinguish distinguish these more than these longer ones.
Yeah, I think that's.
Makes sense. Attention system to produce the count. Ignore MLPs. I mean, we are also seeing this on like these PCS dimensions. Maybe there is like an extra an extra 4 dimension where these are more separated. But yeah. Not MLPs.
No. The most common word length is like 7.
Wait, so what's the accuracy that they have?
5.
Like, where are they showing the accuracy?
The R squared. You mean?
It was like 95 or 95%. Then, if you look at it, yeah, for each. Okay. But is there like a count which is there for the entire model, or are they only having a character count like per layer? Or is it like the last layer's character count estimate is going to be like suppose the model's character count is?
I mean, you have a character count in different layers that gets passed through different layers as it becomes more accurate. And at some point, at some layer, you need to compare it with the line length to do this thing. Right?
Yeah.
And that will happen at some layer. So what matters for this mechanism is whatever the character count is on that point.
Like from the attribution graph, I think you can see like with this first and second in the different layers.
Yeah, like you see it. It does not label which layer is, but yeah.
Okay.
Yeah, sometimes the attribution graphs are messy even there, but yeah.
Yeah, like or sometimes this is often summarizing like things that are on distributed in different layers, and you have different pictures on different layers, and you kind of put them together.
Yeah.
But yeah. Anyway, let's see this. Continuous workers for some attention opposed to the bearing. In all MLPs, okay. Okay. Headphone. Yeah. Under this lens, we see that it has performing a retrieval runner complication matching to a classification. Okay. Has created probes. Could individual heads enter. Yeah. When individual heads implement this behavior, we can break down the behavior of individual heads by this head uses the yeah, it seems like this is going to actually before we keep going with this, should we okay, I'm going to do the thing I said I was going to do early, but then I got sniped by this part. And
I think
before
this is the last mechanism in a way.
I guess we can finish then. Okay.
Yeah, after then there's visual illusions and which is
I'm less interested in the
relatively-
visual illusions part. Like I'm relatively more interested in the paper up to this point.
Yeah,
Okay,
this is
so-
a thing I stopped before and I didn't broke it.
So
Yeah.
yeah, I want to keep
Yeah.
focusing on this part and try to understand it.
Same.
Yeah, sounds
Okay, let's do that then, and we can go to the next part. Okay, so let's try to figure this out. Ignore MLPs. Okay, so they ignore MLPs because they see that they don't matter much for this mechanism. Like the attention head affects the character count representation more, 4 times more than the MLP, so this is an attention head thing, mostly. We focus on attention transformers, the embeddings into the count, and how to layer one for the reference representation. Okay, makes sense. So they have this thing which is the head sum, which is the line character count probes on this dimension and the context position. So, and I don't know what the colors are on this block, but okay.
Inner product of the summed attention outputs and the character counting probes.
like the dotted lines are when the end of the line is.
Yeah. Is doing this. Okay. Head sum probe armax. Through char count. Head sum. So you have a probe and you do it over the.
Wait, is that true? Like, are the dotted lines the places where the line ends? Then why would it be over the context?
I mean, it makes sense. I think it makes sense. That
This
they
is
are.
this is just computing car count. So at like
Yeah.
20, that I think that's when you like are at the end of the line. So your car count.
Oh wait, that's when
resets,
the new line
basically.
is there. It says that in the caption. Yeah, so the dotted line is when they add a new line.
Oh yeah, okay. So yeah, okay. Oh, okay, so that's so the red is the red is like positive activation. The blue is like no activation.
The actual character count, yeah.
Inner
Okay.
product of the sum attention output. So you have the attention outputs, and you do an inner product of that with the probe. You have a probe that counts the characters, and you do the inner product, and it gives you that.
Interesting.
Okay. And then they do this thing where they try to look at the individual heads, and they are doing this thing where they are projecting into the probes, which okay, I'm not sure I completely understand right now what that means. I'm like, I mean, okay, you take the zoom I mean, I guess it's the output of the attention matrix, and then you just do a project. You do either product with the character counting props, but I'm not completely sure I have full situation for what that means.
You know how the straight lines summed into a spiral. So those are the straight lines that sum into the spiral. I mean,
Yeah, no, here it's
helix.
just
What do you mean?
yeah,
Oh,
each
okay.
of these things are sum into like each head sums into yeah, makes sense. But yeah, all right, you're right that these ones are the straight lines.
Wait, earlier
Yeah.
you were saying like you don't know what the colors are. Did we figure that out?
Oh, the colors are the head output
Not in this,
for
not in this previous plot. Is it the same in the previous plot as well?
yes, it's the inner product of the sum attention outputs and the character probes. So they have some probes for each, like they do some the probes outputs the character count, right? It's like a linear regression that outputs the character count, and they do the inner product of that with the output of the attention, like the activations on the attention for that
Or
position.
logistic regression. Yeah.
Yeah, there was a logistic regression. No, I think not sure if it's a logistic regression of the other linear thing. But
I see. Then they should probably swap these two figures then, because they're like in the second figure they have the access for the like the output of the inner product with the attentions or with the probe, but they don't define it like up here.
Line character count.
Like the L0 had some figure, okay, not the one versus the true character count. The L0 had someone versus the head outputs projected on the line character count probes. Like these two figures seem like they're out of order. Like I would put the head outputs one first and then put the L0 head some, just because of that access on the side. Maybe they cut it off.
Yeah.
I think
Yeah,
that
like
the
this
right
access should
one,
be there in the first plot as well.
the right one is just comparing the result with the argmax with like the ground truth.
Yeah, the
So-
right one makes total sense to me.
Yeah. So it makes sense that it would be second to me because it's derived from the first one. In part. Since it's argmaxing
Okay,
the
I see. I see.
first
I see where you're
graph.
coming from. Yeah. I can agree. I think I agree. I'm just saying that access should have been there.
Okay, so they have a bunch of probes, or the probe is the probe is a logistic regression. It outputs higher numbers and lower numbers here, and this is just
Mhm.
doing argmax of this.
Yep.
Okay.
Move on.
I have
I should have trained a crosscoder instead of liner props. Or maybe not.
We can compose the sum amount of the contribution of the positive to the head layer 0. Okay. So this is the different heads, right? And it's the same kind of plot, but for the different heads. And it seems, you head output created on the probes. They're kind of doing some classification where you. So red here means that when there is some line character count and you are in that context position.
So weird.
Yeah, this is a kind of weird plot. I don't know. Maybe we should read the next part. Okay, we recommend the behavior your head players and they obviously quit. Each head uses the previous nailands as an attention sink, such that for some number of tokens after the new line, then the head just attends to the new line. Okay, makes sense. After that certain amount of tokens, the head begins to smear its attention over its receptive field, which goes up to a maximum of whatever tokens. Okay, so For some amount of token position within line, normal average attention to new line. So set head 3, the first 3 heads start attending to the new line, and then they start attending to something else. Right? Yeah. 3 does something else where it attends to new line in the middle. The OB circuit coordinates with the QK circuit to create heuristic estimates based on the number of tokens on the line multiplied by the average token length. Okay, so so that's with a neural net correlation thing. So instead of learning, that part just instead of having all of the counts for each token, they just assume all tokens are around 4 words and just estimate based on that.
That's so funny. I totally missed this part. Yeah.
I assume the model also has additional length correction terms. So maybe there are some tokens that are very long, and they get, if it's very long, it's it's different for add some correction.
Like how long is the token? Like 4 characters. Like yeah.
Pay attention to the new line each head is the average token length multiplied by the head thing size. I think it's easier to learn that having a giant pile. Like the model probably also does have a giant pile of how long is each token, but maybe that learn later, and Pearce learns to have some estimation like this or something.
I wonder if you had if you adversarially selected like really long tokens, okay, that were like at the end of the dictionary, then you kind of inserted them in a line like after a few lines which are like in the same length, whether we would like really confuse the model's character counting because like we are selecting like unusually long tokens.
I wonder if they do that. Like, is that what the visual illusions part is about, or is something else?
Let me check.
Maybe that seems like there's I feel like once you understand this, I feel like there is a few cool things you may be able to, assuming that the latest models have the same kind of mechanics. There's maybe some weird failures you can find that you wouldn't have found otherwise on big models with doing things like that using not very common, very long words or things like that, and breaking the new lines.
Yeah, I couldn't find him like talking about this in the visual illusion section, but maybe I didn't look too closely.
Also, I wonder how good are models if you ask them to count how many words are on a sentence. How many letters are in a sentence?
Oh, I mean, this is just bad.
Maybe they are bad, and they just, even if they are bad like that, they just do the trick of, okay, so words are around 4 words, and that's kind of just words.
Right. Yeah.
That would be pretty funny.
Approximated.
I mean, I would expect a sufficiently smart model. Like if I did this, okay, and what would happen is that like usually I use Cloud Code for like my AI stuff, so it would just like put the message inside a string and then call like stir dot, like len stir. Okay, so like if you put it in a harness, then you can just use the tool call to get the precise number. It doesn't have to use like native perception, although it's only interesting in the native perception case.
Yeah, I think you will have to tell it to not use tools or whatever, or use some version with some harness with tools. But on the web page, it's going to just use the tools. But yeah, I like it. Probably does a bit more, but like there's additional. Then we should keep reading it.
But maybe it generalizes from like so a lot of people might have done like len of something, so such like equals some number. So because it's seen this in the training data like many times that like len of some stir. So if you told it len hello world, like I'm pretty sure it would natively know like the length of hello world,
No,
right? Because this
not
is
really
like
for
the
that. I think like it does this here, but it's probably also learn the length of words because it also will see the thing with new lines that this mechanism is for. Like there are new lines and it's going to have to calculate it. As if it's using for as an approximation, it's going to mess up sometimes and predict a new line where there isn't or vice versa. So it probably does that. I am guessing this additional length correction term is that like for a lot of very long words, it does note that they are longer and used on different numbers.
And then they
yeah,
write
good
later
point.
that finally the OV circuit applies an additional correction depending on whether the tokens in the receptive field are above or below average in length.
Okay, so it does have a big table all over of how long tokens are in practice, but it it probably doesn't bother storing all the tokens or only the tokens that are much longer or much shorter than average.
Yeah.
So that makes sense. That's more efficient. Instead of just storing like all of a big table for the tokens, you just say, okay, if the token is a very long number, you just because you also don't, the model also doesn't have the exact doesn't let most of the time it might be seen like the thing you were saying before of like of Shakehead was saying before of like it's seeing on the internet some examples of people saying the length of some word, but most of the time it's going to have to be guessing and learning from having seen sentences and where they like this and where they end, and so it might get some approximate sense that I don't know if it says some long words like await, it seems that it sentences tend to end earlier when there are a lot of words like this. So it probably it doesn't maybe doesn't necessarily know the length exactly. Just this is a long word vaguely.
Yeah. Average in length. Tokens average in length. I wonder if they mean like the magnitude of the tokens or if they mean the words themselves.
I mean I guess in the number of yeah,
Me too, yeah.
the number of characters in the token.
Yeah.
Although you will need, well, it depends because that only works if you are using normal fonts and all this and writing with normal. If you are writing in Japanese or Chinese with different, or some other language that uses a different writing system, it's probably there is probably some more over complicated things going on there, and with weird Unicode stuff and emojis and whatever. There's probably. There's probably things going on with that. I guess also the text editors need to solve that. I don't know how that works.
Yeah.
This is a similar to use algorithms to count the characters between adjacent neurons. How is the line width saturated? It's possible that the model computes a global line width with taking over the max overall line lengths in the document or uses exponentially weighted moving average of the lines several line lengths. We do know that the line width uses partially distant sets of heads, likely because the attempt of previous licensing mechanism needs the question whether the current token is also a new line. Okay. So yeah, they don't figure out how the model sees that realizes that the line width is 3 by seeing 3 previous, lines and seeing that they are 20. I don't know that they have size 20 like here or whatever. People keep messaging me on Discord. Anyway, Yeah. No, yeah, never mind. Going back to
Exponentially weighted moving average. Would be interesting to see.
visual illusions. Humans are susceptible to visual illusions in which contextual clues can modulate perception seeming. Wait a moment. Okay. Human are susceptible to visual illusions in which yeah, this yeah, well, okay. So humans, yeah, they're confused. I still okay. So before going back to this, I still don't get how you do how this all works. Like okay, it guesses, or I guess you can just add, right? Like if you have the number of tokens, like you can just have without the error correction you add 4 and you just the attention.
Well, last time I made Claude like gave him the paper and give me concrete examples. Plug in the numbers. That helps, but I forgot it.
It has uses a previous neural system. Yeah, I don't completely understand what all of this is doing. I understand the for like uses for as a average token line, which is funny, but but yeah, I still understand what each head is doing and how what these plots mean. Okay, when attention is head up weights the average token length multiplied by the head thing size. Wait, I think I know. Okay, so you make the heads attend to the like you just have the new as an attention sync, meaning you attend the first token attend to the new line, right? And the next tokens attend to the new line, but they also attend to everything else. So like the amount you attend to the new line decreases as you have more tokens, right? Because the attention is more spread out. So you can just use how much the number on the like you have some vector on the new line and you can use the size of the attention on the new line to calculate how far you are from the new line, and then you just can assume that the average length is 4 and multiply it by like some inverse of the strength of the new line. Like yeah, so it could be a negative thing on the new line.
That makes sense.
I don't get why head 3 is the other way around though. But
Would it be monotonically decreasing attention if you add more tokens? Like, because like I can imagine a case where you add a token to a sequence and it changes the distribution so that like the new line sucks up more of the attention, like in total. Like maybe on average it will go down, but I wouldn't expect it to monotonically go down.
but the attention is like the attention adds up to 1, right? So
Yeah, but the first token can like have 0.99, and the rest of the tokens can like add up to like can be the rest.
Yes, but you can do yeah. I guess you do need to shape the numbers in some way for that to happen. But I think you can set up the attention scores so the attention ends up looking like that, right?
Mhm.
You can just make them bigger. Getting Discord notifications. And if I had two screens, I could do both, but it's a bit annoying. The tokens.
There's a way to change your notification settings so that it pops up in like a little corner.
In this context, the probes are on the attention weights, right? Descartes is asking. I think so.
It makes sense. Yeah, it has to be on the attention activations.
Yeah. I'm a bit confused because each head uses the previous new line as an attention thing, such that for some number of tokens after the new line, the head just attends to the new line. So, but if it attends to new line, doesn't it reinforce? Probably not later on.
I don't know. Attributes. Fine.
Yeah, when you put the when you put the probes there, then you get this result of like the head sum probe argmax is like basically fitting the true character count.
I know that, so I understand what is going on with the probes here on each head. Like there seems like there is some separation here where for inside each new line, like for high character count probes are getting high numbers and low numbers. Does it just mean that this head activates on the high character counts?
That would make sense to me.
It just feels like this is a kind of weird way of putting it, and it would be nice if they made another plot like this. Yeah.
Wait, I wasn't paying attention. What do you say?
Does this here just mean like this head activates on high character counts?
Okay.
Like I'm not sure, but I think it might be that, right?
Yeah.
Wait.
Like
does. Yeah. Sorry. Go ahead.
Yeah, it's like the character count probe. So yeah, and the character count probe seem to fit the true character count. So the probe seems to be a good enough representation of ground truth character count. And if all those heads are summed together, then they basically correspond to the true character count approximately.
Well, if you look at the bottom left corner, okay, of the L0H0, there is that red region right over there. So if it was purely blue to red gradient, then it might be a character count, like just talking about L0H0.
Yeah, but because
with this red, then why is the red
well,
there?
This seems also related to the attention sync thing, right? Where it matches with the probable low character counts. I up to the first, 5 or whatever, 10, whatever, and it's red. and this is also like on head 0 is small, which is small, and on head 1 is a bit bigger, which is bigger, and then head 2 is a lot bigger, which is this thing, and then head 3 is doing this other thing. But
Yeah, what is going on with head 3?
Yeah.
I still not completely sure how to interpret this plot, because they're doing the crazy thing where this probably makes a lot of sense in their head, but they are not explaining it that well.
Oh yeah, I want to be head 3. Okay.
Like you can
Head
see
3
how the red is like there's this pattern.
Yes, I don't know. So it's head output projected to the probes. Okay, let's say for a moment we have a high character count on this position. Okay, so we're on some token position. When the character count probe, I guess this is like the possible. Okay, so I guess you have a bunch of probes, or it's really a single probe with some classifier for each number, right? And you try to see which ones match, right? And you're taking the token position because the model is just not counting differently, it's just doing some approximation most of the time with 4. So for each position you see that when the character count probe says the number is low. Yeah, no, I don't understand.
Like you want to get that the wave on top, like the head sum probe argmax. Like you wanna construct that, or like the head sum. So it's like I keep trying to think. Okay, those are like different frequencies that you put together, something like that.
So you have
Like
here
you
these 9 character count probes. So you have this line with those. Okay, this just it's the count matches. But what's this and how you get this from here? So you have the 9 character probes, and it outputs something for each. What is a pointing here? Is a list of examples where for this position the true count is something? No, because there's not a true count, it's the head thing, right?
there is true
So
count. The true car count is the on the right, the blue one.
yeah, but
And
what
yeah,
are the dimensions here? Okay, so here this dimension is the line character count, but here is the line character count probes. So I guess this is each probe for each character. But what does it
Yeah.
mean for each
So they train like
probe?
150 probes, right?
Yeah.
So I understand the setting, and then each single probe is for like a character length. So like there's a 1 character probe, there's a 2 character probe, and so on.
So
Right?
is this you take the sum of you have some vector and you try to project it into the probes, and for each position. Okay, so just have some sentence. Right? It doesn't matter much the sentence because it's saying all sentence or words are for approximating or tokens are for. So for each composition you have the probes for each, like how much it activates projecting into the probe for each number, and you get this thing where it increases over time more or less. Like it's kind of to see, but this matches into, if you do argmax of this, you get the correct line. Okay, so this means here that if you project this head on this position, or like here or here, you increase Oh wait, is this just trying to make this line where for this context the character pros for font is it trying to add four by making like four things where you have slightly high numbers here and high numbers here, like low numbers at the start of context and high numbers on the rest. And here you have low numbers slightly there and high numbers here, and then
Yeah.
kind of this and this, and did you add all of this together and you get this thing?
Yes. Yes.
Okay.
Yeah.
I think I understand then. It just match the okay, just trying to do make a diagonal line where with slope 4.
Yeah, diagonal line is slow for well, but the probes are not perfect. So if they were perfect,
Yeah.
then it would track it like very like granularly. Like every time you add a new token, the probe can tell you exactly how much. But the probe performance
Yeah,
isn't perfect.
but the
Yeah.
way it does it is by adding these four heads, where instead of this head just has a high number for context more than 10 or whatever, and low number for context less than 10. Like, well, it has a kind of wide thing where it's kind of distributed for the along with all the number line. It doesn't match the probes correct match, but it kind of all of this gets added into something that increases the probe
Yeah.
for.
And you can also see how head 0 is kind of inverse of head 3. Kind of.
Right. Head 2 makes a lot of sense in this context, where like I think like head 0 has learned, sorry, head 2 has learned that like okay, if it's like later in the context and we haven't seen a new line, then have a high activation on the ones which are like above 60, like so, and then
Yes.
the probes which are like 40 and below, like if it's behind, let's say 10 in the context position, then you have like a high activation for those. So just like learning these two
I
groups.
think okay, but also head 3, right? Okay, I think I still don't know what's going on with head 3. Head 3 has high for, but I don't know what's going on the first. Okay, I'm a bit confused. No, I was right because this is different concept. Yeah, but you have. I think this head 1 and head 2 are just doing a correction where for the lowest numbers they are decreasing it a lot or something.
Yeah.
It's like pushing each other. Like the first one is pushing everything high, the last one is pushing everything low, and the middle
Yeah,
ones
no, but
are
it's
like
pushing
stabilizing.
everything highest at the first numbers, which is pushing them low.
Yeah.
So yeah, I guess these all are shapes that the model is making a kind of silly way to just make this. It's just trying to make this shape because it can't
Wait.
just.
Maybe head 3 has learned a constant length, where like no matter what position it is, it's always saying that oh, it's between 20 to 80 characters. Okay, the line is between 20 to 80 characters. Like
It doesn't do that for the first new line, which is
yeah, that
weird.
could just be noise.
But yeah, that could be noise.
Like if you look at the 20 after a line break, then it's not, that's not there. So it's only at the very beginning.
Oh, but maybe at the very beginning there is something like the model doesn't know where
Like a
in the
beginning of
sentence
sequence.
is. Like maybe the model doesn't know if at the start, like if it's at the start of the sentence or not. I don't know. Yeah, this could be just beginning of sequence token weirdness.
Yeah. Like at the
That doesn't matter much because it gets washed out by it. but it's low numbers of heads.
And it still struggles. Like if it did the shape correctly, then like the true char count.
Wait. This might be related to the ripple representations are optimal section. The head tree.
I mean,
Because
I
it's so
do
periodic.
we also
Yeah,
do
yeah.
know that the actual embeddings look like this, and this also probably looks like some spiral thing. This 3D, like it's probably we also saw here that doesn't say here these heads are do look like this, right? Like this is the output for the heads. So it's just making the.
Yeah, it's making
So
the
are we
spiral.
just? So are they something like this? Are we just seeing? I'm confused how. So here it seems like like an actual line, right? How do you get from this line to like from this plot into an actual line? Because it feels like it was actually activating more here than in here. But I guess this is the PCA. Maybe that's just the probes are not great. Wait, is this just?
Well, the difference is that this is, as far as I understand, for all possible tokens. I think so. While the plot is like for a certain sentence with certain line breaks, like a specific example.
Yeah.
So like the before one is like much more general, average, if I remember correctly.
Anyway, want to keep trying to figure it out, or do I go to the visual illusions or whatever section, because it's kind of late and I don't know how much people want to stay here.
I want both.
Inverse Fourier transform of that, what it would look like.
Yeah, I was also thinking about that. Like, hey, periodic, let's just throw Fourier transform at it.
Fourier transforms to everything.
Yes.
The thing is, the Fourier transform, I have decided, doesn't actually won't actually tell you the third dimension here.
Yeah.
Maybe the modular addition mechanism uses a third dimension or something, and it didn't. Well, no, because it's still explain most of the opinions. But, yeah, pattern. Like in the modular addition mechanism, you actually don't need a third dimension because it's like the examples here. It's not an interval, it's a ring, so you can just do a circle, and I guess you can still get more dimensions, but you can do something like this, where if you have an interval, I don't know, it's still easy, but if you do circle and you increase the some width, you eventually, yeah, it's kind of easy still, but it doesn't really do a spiral,
Yeah,
right?
I played
But if you
this,
have an
but I
interval,
didn't understand anything. I just like thought the pictures were pretty.
if you have an interval and you have some width of whatever, it does use like a third dimension to separate the lower ones from the higher ones. I want to see like with more points, but never mind. Anyway, so why to quickly look at this? Oh, they explain it more here. This paper has a lot of things. Yeah, I want to do a thing. Let's see everything that is on the paper quickly. So it's visual illusion.
I think I get
Uh,
it. Uh,
I feel like I want to spare, like, I need another day or something. So,
yeah.
but need to stop making so that this really cool big papers. I need to divide it in 5 different papers or something. Nah, it's okay.
Yeah, true.
Related war. Okay, so they do the visualizations and they well, what's the visualizations?
How did they get the symbols?
Okay. When the fight instances which has normal attempt from a new lane to the previous neighbor, we instead attempt to the new lane to the shoot certain string. This of course the limited in the gate diffs. That you mean you want to start your name contact duration other than it. Okay.
Okay.
Okay, so they just have some other separator that is using other context, and the model doesn't have a mechanism of if you see this separate, just say has a look at the previous separator thing, it doesn't have a thing to suppress that separator when you are not in a context where that separator happens. Probably the newer, bigger models will eventually have it, or maybe this already has because it's not like not as much, right? Still
So
79
this
towards.
happens. This happens because the model confuses the symbol for new line.
Yes, because it's saying that in git diff you use this as a new line,
Right.
or like it's
Makes
a
sense.
Every model
delimiter
is
for like
trained on
separating.
like post trained on like code tasks, okay, and so they need to put in like a lot of git commit messages, and inside the commit messages, like in that distribution, like the likelihood that there's like a new line after certain characters is like greater, and so this just reflecting the fact that like, okay, in the code distribution, these things lead to line breaks. That's my understanding.
Bit overgeneralized.
So it makes it think it's in the code distribution because these kind of tokens kind of only come up in that
Yeah.
context.
I see. I see.
Yeah. Okay. So it's code delimiters mostly. They plotted for all different kind of tokens and they get this. Yeah.
I guess this is one way you can kind of weaponize it. Is like, if you're fighting an AI, just like throw a lot of ats at it and it'll confuse it.
Throw a lot of long words to it so it thinks that length is 4. On the number of words in this sentence, 4.
This is the way to pass the Turing test. Like, just take the at, okay, and like see how it reacts.
Yeah.
On the number of R's in strawberry. I wonder if you look at the strawberry thing and found some weird thing like that. I don't know what the problem would be there apart from just tokens are weird and the strawberry there's multiple tokens and it
It's
can
also
be
a
a
scaling
different.
problem. Okay, if you ask, I think is there like what's the strongest model which fails the strawberry test?
All of them.
I don't know. I haven't
Well,
tried the latest
nowadays
one.
they don't. You have to say how many R's are in a blueberry or something like this. And they say 3 because they've been overfitted to strawberry to oblivion.
Yeah, I will ask them if I wanted to test that. I will ask them. I said this before, but I think Shady wasn't here. That I will try with a different letter on a different, or even a different kind of task that implies counting
Well,
letters.
well,
Because
it
now,
says two in the Blueberry. Like I tried 5.1 thinking.
because the specific thing with the R's is already a meme, and you should probably try other letters in other words.
No, I know they don't specifically train on this because my friend in OpenAI is like they said that they, even if it becomes a meme, they don't like specifically.
Yeah, but I mean that there is a lot of text on the internet saying talking about this strawberry thing. And I wouldn't be surprised if, for example, I don't know, the models sometimes get it wrong because they think they are supposed to get it wrong or something.
That could be a factor.
So if I wanted to test it, I would try a different, I don't know, count the number of W in wing or whatever. For example, the word has multiple. The number of G's in suggesting, for example.
The number of E's in Eliezer.
That's another one. Oh, related work. Okay, this is just a bunch of related work. I'm kind of interested in what they talk about. If there is some cool related work things we can read it for your viewing groups. Time breaking. Yeah, some people. There's a bunch of people studying lens. Inner percentage of the organization models of the year, vision models, correlated models. Geometry, grammatical relations, multilingual representations, truth, binding. Calls and represented intervention. Yeah, another thing that there is a con. I need to look into this because I find very interesting this how the structures of the presentations are.
Yeah,
That is
I want to
what you
run some
said?
follow experiments on this paper.
A survey and call to action. Relational composition in other words. Uh-huh. More. Oh, I like this one. A more formal notion of feature manifold and propose the continuous similarity in cause intrinsic geometric features. By testing the theory, they observe highly structured interpretable dotted manifolds that have ripples and direction.
Oh, that sounds like more automated. Or not?
Or like, I think this paper just talks about it like it's more a theoretical paper. And they talk about that. I think they are doing something automated where they are looking at cosine similarity. But yeah, this is just pointed at some direction you could take to make some actual automated version of this. discussion. Yeah.
Whatever is this feature emergence via margin maximization paper is about. Oh, that's pretty old.
So this is perception. The meaning of the model is responsible to seeing the input and much of the early circuit service of sensing and perceiving the text and correlates in vision models into low level perception. Okay. I mean, that's just another way to describe it. For example, the continuum manifold solution optimal materials with incapacity resolution with the connections to separate screening curves and Fourier features. All that I had to do.
So the 49 papers apparently says that the helix-like representations are optimal, provably, in certain settings. So there's like mathematical theory why it's optimal, apparently. Okay.
I mean,
Oh
I guess
god, I would be one-shotted by this. I would turn into a crackpot if I like tried to look into this.
Yeah.
I can just see it.
everything is spiders.
Yeah.
That,
I would become a case of AI psychosis. No.
I think it was the current en el anime now. Ya está going crazy. Oh, also DNA is also a spider.
I used to be obsessed with Spiral. That's funny.
All of us. I think it was like something with magnets.
Maybe.
Feature manifold duality. This is feature. Yeah, I mean, so far the way they did the actual, it was interesting, and they learned a lot more from the other things. But it seems like to me that it was right now it was much easier to figure out, and even for our NAS to us for understand it, to figure out just the attribution graph and the whole other stuff with all of the geometry.
Yeah.
Yeah, this is an easier paper than the attribution graph paper. I agree.
The complexity task. Yeah, this is just the thing that we were saying the whole way, that someone needs to find some way of study this without having to manually manually do this. I mean, I guess they already have something automated for this kind of. It's called PCA, but we need something more automated than that.
Something that
Because
will find the
no, the thing is, things where I try to do PCA on representations that later that doesn't help that much. Sometimes. Or like maybe it helps if you are better than me and okay, so this is just the appendix. That's how much. There's a lot of things. Oh yeah. This is for different K.
The organization of the features on a low-dimensional manifold is an instance of a common motif in biological cognition.
Also, it does seem
Okay.
this thing what we were talking about was just noise because it doesn't happen on these other two
Hmm.
on
Yeah.
the head thing. So it just was seems like it was
But the
just
ripples,
some.
yeah, but this like, yeah. So the head to, okay, this is interesting. You see for one of the prompts, I am assuming that like each row is a different prompt.
No, it's a different size of different case, which is the different
It's 40 in
length.
all of them, no?
Line width?
Oh wait, no, sorry. Okay,
Okay,
what is
I
like?
think it's different prompts anyway. Like it is different.
Yeah.
It's different language
Yeah, what is
Different
K?
different.
line width.
Actually, yeah,
Okay,
not
is
sure
like
what
the
it
length of like the line.
Since you can see the context position, like the difference between all those graphs is when new lines happen. You can see on the top it's much more frequent.
Frequent, yeah. So over here, this when you have like shorter lines, this really confuses head to.
Hmm.
Head to does well with like bigger lines.
Oh
Mm.
yeah. Yeah, because it only starts. Yeah, it only starts outputting higher with more than certain amount, so it's not. It can't. Doesn't fit here.
Oh wait, no, but this is basically correct, right? Because if you have line breaks very frequently, then you can never have enough tokens to kind of build up a very
Oh,
long sentence.
oh yeah,
So
that makes
this is
sense.
what it should be.
Oh yeah, yeah, I think you're right. The rest is just links to the. It's just a little bit more.
I really like the alternate paper title section.
Oh, where?
The alternate paper title section.
Oh,
Yeah,
read the
this is
title
like,
here.
yeah, this is when I first read this, I was like laughing at this. Yeah.
New line. Aterrizate the end of the line. The end of the line. Very uncertain. When is the store boring and love the carriage return? Bringing out the lame mechanism. We found a GPS instead of GPT. Okay, yeah, that one is kind of bad.
Yeah, it's not fair. These are pretty good puns.
I wonder if they ask Claude to generate those or just they were the ideas.
Possible.
Yeah, so I guess that's it. We can go to some specific part that you want to revisit, or we can just end it here because we were being here like 4 hours or something.
Damn.
I still wanna understand the physics model, but not sure if I have the brain power.
I mean, it's a physics model that isn't just this thing that that things attract and
Uh,
repel.
the context before it.
Huh. Oh yeah, this part I still don't
Yeah,
completely understand.
exactly.
Uh, wait, we will try to understand the line. Okay, so
Yeah, this
we
is something
could,
which I'm also curious about.
yeah, we were. I think we were here before you came, and
Yeah,
we were talking about this, and we didn't figure it out. Okay, so we have this. This is structure turns out to be a natural question. So this the size percentage of similarity. As a toy model of this, so what is toy model? Suppose that we wish to have a discretized circle worth of unit per. Okay. It's similar to its neighbor, but orthogonal to those further away. Okay, this can be realized by a symmetric set of unique vectors with a cosine similarity matrix X picture below left. So this one, right? I don't get. Well, yeah, okay. So in this one, it's okay. I was reading it wrong the last time. So this thing, each thing, each of the vectors is similar to the one adjacent to it, and then slightly similar to the next one, and so on. And then it just drops to 0 immediately after like try to see the length of the pixels are supposed to be here, but like 1 or 2, right? Okay.
So is this like when you go in person to a place, then like you are next to people who are similar to you? Or
Okay, what does it? Symmetric set of unique vectors with cosine similarity is printed here. We can think of the original vectors. Okay, so I don't know how that. I was thinking of they are orthogonal, but they can't be all orthogonal because they are similar to the closer ones. So they're saying that that this is easy to do with more dimensions. Okay. So they then have this super, like 150 dimensional curve where the vectors are close together, but and yeah, so the 150 dimensional curve where the vectors are close together. Also, I noticed that on the corners they are similar, so that like these are similar to the 0. The middle is similar to 0, so it's like a circle. Like they are, it's close. It's not an interval. So they are talking about them projecting this super complicated 150 dimensional curve to five dimensions, projecting it to the top 5 eigenvectors. I don't sure I have a good intuition of what.
Oh, projecting. By projecting, they mean like dimensionality reduction.
Yeah.
Okay, that changes everything. I thought projecting means like projection in linear algebra.
It's not the same. Are you if you do progression in linear algebra, don't you still get less dimensions?
You can, but you don't have to. It's just matrix multiplication. It depends how many dimensions the matrix has, as far as I understand.
But you can see it as like if you multiply by you project it to 5 dimensions to you do multiply a matrix multiplication with some other vector that has that it's like 5 orthogonal dimensions. You can see it as changing it to that basis, right?
Yeah.
So you could, if you have it in that basis, you could think of that basis as 5 dimensions, and that's it.
Yeah.
So matrix multiplication, you can see it as dimensionality reduction if you have vectors that are orthogonal to each other that form a basis.
Yes. Huh. Let's see how Claude explains
Yeah, I feel
it.
like I need to review basic linear algebra one of these days. uh, we also see it ringing. So they also the three eigenvectors, so us poor humans that can only perceive three dimensions can see them. And we can think of the original 130-dimensional embedding of the circle as being highly curved. Yeah, I don't. My brain that can't imagine curves in 150 dimensions, but okay. And the resulting 5-dimensional embedding and retaining as much of that curvature as possible. This manifests in ripples in the embedding of the circle within a 3D progression. Foreign analysis and analytical construction. So there is some, yeah, it is related to the foreign analysis. Suppose when we wish to have a discretized circle worth of unit vectors is similar to its neighbor orthogonal to those further away. The cosine similarity matrix address will be circular, well, whatever that means, just this thing, yeah. The columns of the square root x of x are m vectors, where n is the number of discrete points of the circle. Yeah. Okay. Yeah. Wait. What is where?
Yeah, that makes
Whose
sense.
produce the similarity matrix? Huh? Uh. Yeah. Now suppose we would like to find vectors in lower dimensional space whose similarity matrix approximates x. Wait, sorry, this. Like the model does for character count. The best k-dimensional approximation of this similarity in an L2 sense is given by taking the decomposition of x and truncating it to the top k eigenvectors. I don't understand why, but okay. Math. The square root of the result will provide n vectors in k dimensions with the corresponding similarity pattern. If pi k is the projection of the span to the top k vectors, then the images. This is something that probably makes sense if you think about the what something being an eigenvector means, but yeah. Let me see below that there's certain global matrix asking. Oh, they have a collab notebook for this. Not going to spend that much time. We're kind of tired now, but yeah. If you were interested in figuring out, you can use this, I guess.
I have
Yeah,
code
it
how
is
they
nice.
construct it. They start with a similarity matrix. They eigen decompose the matrix. Alright. They just take the k dimensions, only the top k eigenvectors and the eigenvalues. And this is the best scaling approximation in the least square sense. Right.
This can
This makes a lot of sense. Yeah.
Recover the embedded vectors to get actual k-dimensional vectors whose inner products give this similarity.
What's this? Oh, it's the break. Whatever. Okay.
Eigenvectors are
Okay.
exactly the Fourier basis vectors. That would make sense. So the top k eigenvectors correspond to the lowest frequency Fourier modes.
But that's only on these kind of shapes, right?
When there's the periodicity that you can decompose. The Projection is essentially keeping the low frequency components and discarding high frequency ones. Which is why you get smooth ringing rather than sharp cutoffs.
I did notice that we had some model. We're looking at one on the modular multiplication thing. We had one model that has like one layer transformers, one with layer norm and one without. And I noticed it was smoother on the one without layer norm, and I wonder why. I guess the layer not normalize it later, so maybe it can get away with level. Yeah, I guess it's probably something dumb like that. Kind of. Do we? I guess we actually went through the entire paper now. So do we? We could end it here if you want, unless you want for me to go to something specific or say something.
No, I need to like eat something.
Yeah, I also should go eat soon. So yeah, I've been here for like since 5, and we're at 9. So yeah. And also
Great
the
paper.
recording is probably getting pretty long. Yeah. So wait a moment in case I don't know. Maybe
This may be probably currently my favorite Mech Interp paper. It has everything. Cross-layer transcoders, attribution graphs, analyzing concrete circuits, helices.
I'm getting inspired to stuff on the modularization for the multiplication stuff.
Yeah.
Where I had a part of the model where I was saying, okay, this is just a pile of like a big table of if it's these combinations of things, this happens, but there's probably some geometric structure there. I don't probably not going to focus that much on that because I was investigating something else, and I don't really care how that is computed that much because I care more about an early part under tension. But yeah, never mind. Anyway, let's stop here and go have dinner or whatever. I'll stop the recording now unless someone else wants to say something.
Okay.
Anyway, let's stop the
Thanks
recording.
for organizing and for going good paper.